Okay, so we'll calculate one more commutator just for the practice. So let's calculate the commutator between p mu and n nu rho. So we'll start off, we've got x mu. X mu is equal to, so we've got x naught, x1, x2, and x3. And that's with the index up. If we've got x mu down, this is equal to x naught minus x1 minus x2 and minus x3. So if we calculate something like d mu up x alpha up, this is nothing but d by dx mu onto x alpha. And you can see we're differentiating a coordinate with the index up with respect to a coordinate with the index up. And this just gives us delta A mu, alpha mu. So please go ahead and check that. If, on the other hand, we calculate d mu x alpha with the index down, now we're differentiating with respect to a coordinate with the index up, but we're differentiating a coordinate with the index down. And you can check that this is equal to eta mu alpha. Eta is the Minkowski metric, so it is a diagonal matrix. And I'm just going to tell you the diagonal elements. It's 1, minus 1, minus 1, minus 1. Okay, so I'm going to use these derivative formulas freely. So when we differentiate with one index down and the coordinates of the index up, we're going to get a Kronecker delta. So remember that, please. And when we differentiate and both indices are down, we're going to get the Minkowski matrix, eta mu alpha. Okay, so I'm not going to keep these now. I'm just going to assume that you have committed these formulas to memory. Not so difficult. If we're differentiating, there's an index up and an index down, it's the Kronecker delta. If we're differentiating and both indices are up or both indices are down, then it is the Minkowski metric. Good. Okay, now let's take a look at the commutator that we want to calculate. So what do we want to calculate? We want to calculate P mu m nu rho, and we'll act on a function f minus m nu rho onto p mu, also on f. Okay, so what is this equal to? Okay, so let's just plug in the expressions that we know for our generators. So we've got minus I d by dx mu, great. And then for the m nu rho, we'll have I x nu d by dx rho minus I x rho d by dx nu acting on f. So this is the first term. And then we've got the second term minus, well, no, I'm not going to spell things out so carefully. I'll just say x nu d rho minus I x rho d nu. And what are we acting on? Minus I d mu f. So the second term sitting over here corresponds to that second term sitting over there. Now, when you evaluate this, there are a whole lot of terms that vanish. The terms that vanish are all of the second derivatives of f. So I'm not even going to bother to write them down, okay? But you should check this. So you should write down all of the derivatives and make sure that what I'm saying to you now is correct. I'm going to write down very few terms, but these are the only terms that survive, and I'll tell you what I'm writing down. So first of all, I'm going to write down the term when this derivative hits onto the x nu. The minus I times by the I is a 1. We've got d mu down acting on x nu down. This is going to give us an eta mu nu. And then we've got a d rho on f. Then we've got a minus I times a minus I. So now I am looking at where this derivative acts on this x rho. So a minus I times a minus I is a minus. The d mu down on the x rho down will give us an eta mu rho. And we've got d by dx nu, so d nu acting on f. And how can we write this? Well, this looks like I times by eta nu mu, and then we've got minus I d rho. This will be acting on F. And then we've got, let's say, minus I, so the minus, sorry, let's say a minus. Good. And then we've got eta mu rho, eta mu rho, and then we've got a minus I d nu sitting there. And you can see in the second term, the minus times the minus I gives me an I, so I times an I is a minus, so it agrees with the sign in the first term. But you see, what's nice is I can now write this as I eta nu mu, and then minus I d rho is p rho, and then we've got minus eta mu rho, and the minus I d nu is just p nu on F. So this is the answer for this commutator. I can now drop F's on the two sides, and what I've got is, this is I eta nu mu p rho minus eta mu rho p nu. Good. Okay, so this was the only commutator that I wanted to calculate with you. The last commutator, I'm just going to quote, and you should go ahead and check it. Who knows? Maybe I got the sign wrong, so please do check it. Make sure you agree with the answer that I'm going to write down now. So let's put the answer down. This is equal to I eta mu mu m rho eta minus I eta mu rho m nu beta minus I eta beta mu m rho mu plus I eta beta rho m nu mu. Now, when you see an answer like this, you should be able to do at least a few checks immediately. So what kind of checks can we do of this? Well, if we look at our expression for m mu nu in the black box just sitting above this computation, you can see that it's antisymmetric under swapping mu and mu. So the right-hand side of this commutator should be antisymmetric under swapping mu and beta, and antisymmetric under swapping nu and rho. So let's first of all look at the mu beta antisymmetry. So if you look at the term at the top and the term at the bottom, to go from this term to that term, I swap mu and beta, and you can see there's a sign change. And to go from the top term down to this term, I swap mu and beta, and you can see that there's a sign change. Then from this term sitting over here, it should be antisymmetric in nu and rho. And you can see if I go from the first term to the second term, and this way, I go from mu nu to mu rho, and m rho beta to m nu beta. So that's just swapping rho and nu, and indeed there's a sign change. And in the same way, if I go in this direction, I'm just swapping rho and nu, and again, there's a sign change. So one immediate check that you can see of this is that indeed left and right-hand side are antisymmetric under swapping mu and beta and nu and rho. So that's the first check that you would think looks promising. So anyway, but you check it by hand. You make sure that it is in fact correct. Now, this is the Lie algebra of the Poincare group. And we have obtained this purely by writing down what the symmetry transformations were. And remember, we wrote down the Killing equation. That's what the coordinate transformation had to satisfy. Then we solved the Killing equation. Then we thought about Lie groups using those Killing equations that we had solved, and we were able to completely characterize the Poincare group, and now we've obtained the Poincare Lie algebra. What we're going to do next is we're going to write down an equation that characterizes conformal transformations. Then we're going to get the conformal killing equation. We will solve the conformal killing equation. And once we've done that, we'll be able to get the Lie algebra for conformal transformations. That's what we're going to do next.